Hello students, today is our second lesson in chemistry and we are going deep into the chapter of matter. So what is density? So my question towards you is, which one is heavier? The one brick or the one feather? The answer is obvious, right? The brick is much heavier than the feather. Now, the second question is whether the 1 kg of feathers will take more space or the 1 kg of bricks will take more space. So obviously the feathers of 1 kg will take more space as compared to 1 kg of bricks, though 1 kg of bricks is heavier. So why is that? This is the reason because of the change in value is the feathers are much less dense than the bricks. Okay. So what is density? Density is related to the two units of matter which are used to describe the matter, like the mass and the volume. What is mass? Mass is the amount of matter. We already know, and the units we use to describe matter is describe mass is grams or kilograms, right? So what is volume? The volume is the space of matter that it takes up. Okay, and the most commonly used units are milliliter for the liquid things, and the centimeter cube or meter cube is the unit for volume for solid materials, right? So this is the most commonly used formula that we use for calculating density. So density is nothing but the amount of matter per unit volume. So it is mass divided by volume. Now let's compare the two materials of different densities. Okay, let's start with the air, which is plenty of us which we can't see but we can feel it, right? So for 10 grams of air, we will have more than 8 liters of volume. So this is the thing, and what you can conclude about 8.3 liters of volume is that it takes more than 4 2 liters of Coke bottles. So the space you can imagine, that is the 2 liters of Coke bottle each. The 2 fours are 8 liters, but it is 8.3. So it is more than 2 liters of Coke bottle size volume can be occupied by only 10 grams of air. Okay. Now let's compare with another material. This we call it as lead. We use mostly for the pencil leads. We use it for making the pencils, and for this case here we see that only 10 grams of lead occupies 0.9 centimeter cube volume. So what you can see here is the difference in units of volume of the two cases. One is the air, that is the gas, and one is the lead, which is a solid. And in this case it's liter, and in this case it's centimeter cube. So we need to find one common unit in order to compare the two materials, that is air and the lead. So this is the unit of conversion we need to remember, that is 1 milliliter of liquids or gases will be equal to 1 centimeter cube of solids, which is a lead example here. Okay, so this you will remember. Now if you convert this centimeter cube to milliliters, you can see that it is less than even 1 milliliter, and liter means far higher than milliliter, right? So if you compare the 10 grams of air versus the 10 grams of lead, you can imagine the difference. We can imagine the difference. It is less than even 1 milliliter of volume. So what's your conclusion now? So conclusion is that the air is less dense than lead, right? Because air occupies a big volume. So volume is more, that means the density is less in this case. So let's use one example or numerical to understand more about density. So this is your question, that is, calculate the density of a cube of copper which has a volume of 16.7 centimeter cube. In short, we can write it as Cc. So the volume of the copper cube is 16.7 centimeter cube, and the mass of the copper cube is 150 grams. So you can imagine this is the cube of the copper and the volume is 16.7 centimeter cube and the mass is 150 grams. So we will use the formula as described before, that is density is equal to mass divided by volume, right? And we will use that density is equal to m by v, which is equal to 150 divided by 16.7, that is the mass divided by volume, okay? And this comes to 8.98 gram per cc. So 8.98 gram per cc is the density of this copper cube, which has a mass of 150 grams and a volume of 16.7 centimeter cube. Sometimes it is possible that it is given that only one side of the cube, then you need to calculate the volume, like what is the value of volume of a cube, that is side into multiplied by side. So side times side times side, we can calculate the volume as this one. And sometimes it is directly given as centimeter cube. We'll solve more numericals later on during the class hours. About the phase change. So what is phase change? Phase change is nothing but the transformation from the solid to liquid and liquid to gas. Okay, so we know that these are the three states of matter, which are the solid, liquid and gas. And let's take a more common example like water, okay? And solid happens when the things are relatively colder. Now, if we add, for example, the heat, so the solid state happens when the things are relatively colder, and then we warm up, we go to the liquid state, and we further warm up and we get to the gaseous state, okay? But for solid state of matter, we call it as ice, and for the liquid state of matter, we obviously call it as water, and when it is a gaseous state, we call it as the vapor or the steam. So why the ice is colder, or why it is solid, and how the change of state occurs? So this is our question that we need to explore. So for example, this is the water molecule I'm trying to draw. So this is the oxygen atom, and we know the formula for water is H2O. So there are two hydrogen atoms and one oxygen atom. And this is the bond between the oxygen and the hydrogen, and it has an angular structure. It is not a linear structure, okay? And the thing that we need to understand that these two atoms are different and they have different properties, right? Like the size. And also there is an important property that we need to remember, is that the electronegativity property. Here oxygen is more electronegative. What is electronegativity? We know that the atoms are surrounded by electrons, right? And every atom has a tendency to attract the electrons towards itself, right? And this attraction can be different for different atoms. So oxygen have a different tendency, higher tendency to attract the electron towards itself as compared to hydrogen. That is electronegativity. So electronegativity is nothing but the tendency to attract electrons towards itself, okay? And hence this bond is an electron, right? So this electrons, whatever electron is there, oxygen has a more power, is more powerful to attract that electron towards itself, and hence what it happens, it develops a partial negative charge on the oxygen atom. So there the delta is a very partial, is a very minute, but it has a partial negative charge. And similarly there are partial positive charge developed towards the hydrogen atoms. So this is the property that we need to remember for every water molecules we have here. Okay. And now if these molecules have very little kinetic energy, that is, they are not moving around the whole lot, then what will happen? The molecules of water will be very close to each other. Now we are thinking of the solid phase or the ice phase. So what happens? The two water molecules are very close towards each other, right? So these negative charges on the oxygen atom will be attracted towards the positive charge on the hydrogen atom of the other water molecule. And we need to think that how the water molecules are interacting with each other. So for example, this is another water molecule. So the hydrogen needs to be near this oxygen because both have the opposite charges. Okay. Now these hydrogen bonds, so there forms another bond between the, for example, here I have drawn three water molecules. So there have been formed the bonds. So this type of bond we call it as hydrogen bond. So these hydrogen bonds starts forming between the molecules, and they form a lattice-like structure. So if you see, the blue one is a hydrogen bond which is formed between the water molecules when it is in a solid phase, because when the solid is solid, the molecules are very close towards each other. And I have shown you one lattice structure. Actually, the lattice structure in ice looks somewhat like this. The red one is the oxygen, the two blue balls are the hydrogen, and the hydrogen bonds are the white, you can see the white lines, they are the hydrogen bonds. Now what will happen if these molecules don't have a lot of kinetic energy, because they are in a solid phase, they are very tightly close towards each other, and they doesn't have much kinetic energy. So what will we say that is about the average kinetic energy is low? What will happen towards the lattice structure? So we need to remember that whenever there is a lattice structure, they have very less space to move around, and hence the kinetic energy or the average kinetic energy will be lower. Okay. Hence these molecules will not move relative to each other, just like the ice. In other words, they are forming a fixed structure. Here we call it as lattice structure. Now what happens if we add kinetic energy? So we are adding the kinetic energy in the form of a heat. So we are warming up the ice. It increases the vibration of each molecule from left to right. So here each molecule of oxygen will vibrate, each molecule of hydrogen will vibrate, and this goes on. So the kinetic energy is expressed actually as the vibration of the molecules. So this is an example where we can see how the molecules of water vibrate. So for example, the red one is the oxygen and the white one are the hydrogen. So they vibrate whenever we add heat to the water molecule. So each water molecule in the lattice structure of the ice starts vibrating. So what we can conclude is that heat increases the vibration of each water molecule, right? So this is a conclusion because then we have to understand that, for example, this is the water molecules, and each have some delta minus or the partial negative and positive charges, and we will see that each water molecule starts to vibrate on its own because of the addition of heat. And so what do you think? What do you think about the hydrogen bonds? So as a result of this heat, because they are vibrating, they are moving to and fro, each hydrogen atom, each oxygen atom. So what will happen is that this hydrogen bonds, whatever is there, they start becoming weaker because they are vibrating harder and harder because of the addition of heat, right? So, but the hydrogen bond will still be there. It will not be completely absent, but it will become weaker because of the increased vibration of the water molecules because of the addition of heat. Okay. Due to the weakening of hydrogen bonds, What do you think can happen about the molecules? The molecules are vibrating, hydrogen bonds are becoming weaker, and as a result, the molecules start moving apart from each other. So the distance between the water molecules increases, and hence we need to remember that the vibrations are still there. The vibrations are very strong, but they're not strong enough to completely separate the water molecules. So what happens is that the molecules start sliding on each other. So the molecules will slide on each other, but the hydrogen bonds will still be there. For example, if we compare the structures between the ice and the water molecules, so this is the gaseous phase, solid phase, and this one is the liquid phase. So here both the cases the hydrogen bonds are present, but here the intermolecular space is much less because it's a solid, and here the molecules are moving apart from each other, but the proper lattice structure is not there because the hydrogen bonds becomes weakening. Here it is very weak. Okay, so now if you add more heat or more kinetic energy, what is going to happen? Can you think of that? Because more energy means that we are adding more vibrations, right? So they are completely going to separate from each other. The molecules are not touching each other and independent, especially if they are ideal gases. So if you can see, we have added the heat, and the vibrations have increased, and as a result the molecules are moving apart from each other. It's hard to see a gas. Why? Because the molecules are far apart from each other. They are not acting just like the liquid and the solid, right? And if we keep making that extended further, like generally solids are more dense than the liquid. Exception is the water, of course. We'll come with an example later on. But solid ice is less dense than the liquid water. And hence this is the reason that the ice floats, so the ice doesn't touch the bottom of the sea, right? So water has an anomalous property which we'll discuss later on, but generally the solids are more dense than the liquid, right? And how do we measure the amount of heat that it takes to do the change of state? We'll see that with the help of the phase change diagram. Okay, so phase change diagram is, for example, this is the axis. We need a two axis. One is the x-axis and one is the y-axis. We'll be plotting the heat versus the temperature. So the heat is denoted by the letter Q mostly, and on the y-axis we'll plot temperature. But before that, we need to remember that the energy, for example, this heat energy, and also other forms of energy like potential energy, kinetic energy, and even in some questions we can encounter the word enthalpy. Enthalpy, all these are forms of energy, and they have the unit of joules. Okay, so generally what is energy? Energy is the capacity to do work, right? So in x-axis here we will plot the heat, and y-axis we will be plotting temperature, but don't get confused with the words like enthalpy, because it's nothing but a form of energy only. Okay, for now. Now heat is a form of energy, and as I add heat, the molecules or vibration increases, right? So what's expected? So let's start from this point, and here the higher the kinetic energy, or higher the average kinetic energy happens when we add more heat, right? And more vibrations happens as a result. So something very interesting happens. We have taken the example of here as water and or the ice. So here the ice, we know that the temperature or the melting point is 273 Kelvin or 0 degrees Celsius, right? So we keep on adding heat to ice, and at 273 Kelvin the ice starts melting, right? So what happens here, this point is very crucial because something very interesting happens. So the material we have taken is water, and ice starts melting, and we have started to kept on adding heat. The temperature does not go up. So this is the important phase where the temperature does not go up for little time, for little period. The temperature remains constant. And this region, the process, we call it as melting. So this is the whole process where the melting process is happening, okay? And we keep on adding more heat, more and more heat. So what happens? So we keep on adding more heat, and then we see that there is a rise in temperature. So each point there is a rise in temperature on the addition of the heat, okay? And then again when we reach the boiling point, so what's the boiling point? We know that boiling point of water is 373 Kelvin or 100 degrees Celsius, right? At this temperature, the water will vaporize, or the water boils. But again, something really it happens because all the molecules are kinetically very active, and just like the solid, so liquid phase change, some quantity of energy is used in this process for vaporization. So here the process of vaporization is going on, and in this red color, the process of melting is going on, but there is no change in temperature, but there we keep on adding heat. We'll come back to the micromolecular aspect later on, but just for now, for the graphical representation, you must understand that this happens, and this has been experimentally verified. So at this point, 100 degrees Celsius, the water turns to vapor, okay, that is the gaseous state, but it is not getting hotter. So the temperature remains constant. We keep on adding heat, okay, and then finally, after some point, after, for example, this point, the complete steam formation have taken place. So no liquid is there. The complete vapors have been formed due to the addition of heat. Now, what's the purpose of heat in some parts of the graph that we need to understand? Because there we cannot see the change in temperature, right? So this is actually the heat of fusion. We call it as heat of fusion, and heat is used to break the hydrogen bonds. So we have seen that there are hydrogen bonds in ice, right? So the heat is used to break the hydrogen bonds and pull the molecule apart to form a liquid water. So here we will remember that, for example, this is a point A and point B. So here the energy or the heat is used converted to kinetic energy, because the kinetic energy means more movement, and hence the temperature increases, right? And for B and C, for example, this is the C point. Here there is a phase change happening. That is, the heat is used to add the potential energy of the systems. The potential energy of the system increases, and hence the heat is required to pull the molecules apart. And it's the weakening the hydrogen bonds, increasing the vibrations between the hydrogen or water molecules, right? And for example, this is the C and D, this is the D point, and again this energy or this heat is used to increase the temperature. That means we can see that this heat is converted to kinetic energy. So here it was kinetic energy, here it was the change in potential energy, because the potential of each molecule is increasing because of the addition of heat. And here again the heat is transferred to kinetic energy, transformed to kinetic energy. And again, similarly here, if you see wherever there is a phase change, the heat is converted to potential energy, right? And because there is only energy is used to dissociate from each other, so each molecule will dissociate from each other and form vapor, right? And here EF is similarly, the temperature is converted to kinetic energy. So the temperature is converted to kinetic energy at A, B, C, D, and EF, and the temperature, heat is converted to potential energy at B, C, and DE, wherever there is a phase change. Okay. So 0 degree may not be the temperature of the ice. So you can see that 0 degree, if we see or think of a 0 degree Celsius, we can think of, okay, it is the ice. We can visualize our ice, but it is not like that. 0 degree can be a temperature of the water as well, which didn't yet convert to ice. Similarly, for example, whenever we think of 100 degrees Celsius, it must be a vapor, just at the boiling point. So it is not like that. 100 degree or the 0 degree, 373 Kelvin can be the water state as well, which is yet to convert to vapor. Okay, so here this we call the heat of fusion, because this is the heat that is required to make the process of fusion possible. That is, from C to B, if you see the point from C to B, the water changes, the liquid state changes to solid, right? So it is fusing, it is fuses. So we can see that the heat of fusion is the heat required to, or the heat that needs to be removed from the system to convert it to a solid state. Okay, because this direction, if you see, we need to remove the heat, and if you see this direction, it is the addition of heat. Similarly, if we see this DE phase, it is the heat required to transform the specific quantity of liquid to vapor. So this is the heat. So here there is a change in potential energy. So the heat energy is transformed to potential energy at BC point and DE point respectively. Next, we'll learn and calculate the quantity of heat, solve problems, or how much ice we need for making our drink cool. We'll see with examples. Okay, we'll discuss some numericals based on specific heat, heat of fusion, and heat of vaporization. So let's see the proper definitions of what is heat of fusion. So heat of fusion is the quantity of heat, right, that is necessary to change 1 gram of solid to 1 gram to liquid with no temperature change. So if you recall the graph here, so there the change in state, that is the change where is happening from B to C. There is no change in temperature, but there is a change. We require a heat. So this heat we call it as heat of fusion, and the quantity should be to 1 gram of solid. Okay, this is also called the latent heat or the latent heat of fusion, and the SI unit will be joules per gram. It is also used, we use calorie per gram, but per calorie per gram unit is not the SI unit. Okay, so what is heat of vaporization? Heat of vaporization is the same thing, is a quantity of heat that is necessary to change 1 gram of liquid to gas with again no change in temperature. So that's very important, the key word that you need to understand, that there is a no change in temperature, but there is a heat that is required for the phase change, and this energy or the heat is actually converted to the potential energy. It increases the potential of each molecule of water, or in that case, that example that we have discussed. So it is also called the latent heat and sometimes called the latent heat of vaporization, and also the same, the SI unit as the latent heat of fusion is joule per gram, and calorie per gram is also used for the other units. Now, what's specific heat? Specific heat is the quantity of heat per unit mass, okay, required to raise the temperature by 1 degree Celsius. So here it is a property of every substance. So for example, water have a specific heat of a certain value, and that value will be different from that of, for example, alcohol, or if, for example, if we take a copper, or if we take any other material. So this is the property, and it varies from materials to materials. So this is the heat required per unit mass, and it raise the temperature by 1 degree Celsius. So the temperature change should be 1 degree per unit mass. That quantity of heat is specific for specific materials, and the SI unit is joule per gram per degree Celsius. Okay, let's take an example. Suppose you have a container and you add heat to increase the temperature, but how much heat you add to increase the specific temperature? So there is a formula to calculate it, and the quantity of heat Q, here the quantity of heat, that symbol is Q, and this Q depends on a few things, okay, and that is how much you want to increase the temperature. For example, the delta T, here we have used the T for temperature. So how much you want to increase the temperature? The more you want to increase the temperature, the more heat you need, right? It also so delta, as I mentioned, that is a change in temperature from T final minus T initial. Okay, so we need to understand the change in temperature, not only the temperature of the system, but how much change it is making. So this heat, the Q, is also depends on what is the material you have. In other words, or what is the mass of the material that you have. For example, uh, more the mass, more temperature or more heat you need to increase the temperature, right? So we can say that the Q depends on the mass. It also depends, the Q depends on the one more important thing that we call, just now mentioned before, that is the specific heat of that particular material. That is what material we have taken. For example, if we have said that if we take water, the value of Q will be something. If we take some other material, the value of Q will vary accordingly. So different materials will be harder to increase in temperature than the other materials. So here C, the specific heat, is the property that we need to remember that is important for finding out or calculating the total quantity of heat required to increase a certain temperature. The quantity of heat required, it will depend on how much temperature you want to increase, what is the mass of the material or how much mass you have, and also finally the specific heat of the substance. So many materials may be harder to increase the temperature and the other materials, and it will vary. So you need to understand that this Q is equal to MCAT. This is a good way of memorizing this particular formula. M into C into temperature difference, and this formula will use much more. So let's get into a more specific example. Let's see this example, like what is the quantity of heat required to raise the temperature of 2 kilograms of water from 20 degrees Celsius to 50 degrees Celsius. Okay, specific heat of water is given as 4186 joules per kg degree Celsius. So this is given. So for example, this is a water body which has where we provide some fire, outside heat energy, and which is we need to calculate the Q. Okay, and the mass of the water body is 2 kilograms, and the specific heat is 4186 joules per kg degree Celsius. So it's given. Okay, so this is a quantity. This is the property of water. Now, what is the value? What can you understand from this value of specific heat? So this is at room temperature, the specific heat at room temperature. So let's get an idea about what's the meaning of specific heat in more detail by seeing the value. It means that the water requires 4186 joules. Okay. To increase just 1 degree Celsius if the quantity of water is 1 kilogram. So 1 kilogram of water requires 4186 joules, and we have to provide this quantity of heat to just change the temperature by 1 degree Celsius. So this is a huge quantity of heat, right? And hence we can understand that the water has an ability to store a lot of heat energy without raising its temperature by much. Okay, so let's do this example. Here we have seen that we will use the same formula of Q is equal to MCAT. Okay, and here we know that the Q, the change in temperature is from 50 to 20 degrees, 20 to 50 degrees Celsius, right? So the change in temperature will be 30 degrees Celsius. That is we have to do the simple subtraction or difference. And here if you see that Q is equal to 2 kilograms into multiplied by 4186 multiplied by 30. So need to be very careful. So mass is in kilogram, specific heat is also in kilograms, and it is in degrees Celsius. Okay, so here we have to calculate the Q, and it comes out to be 251,160 joules. So you can understand, right, why So this quantity of heat is a lot of energy. It just takes change of temperature to 30 degrees Celsius. So 30 degrees Celsius change in temperature difference, we need to this quantity of heat to just make a difference of 30 degrees Celsius. So let's do a complex example, because this was a pretty simple example. And let's say that instead of heating the water by fire underneath, we just take a hot piece of metal. So we take a metal of copper, and which has a something temperature, which has a specific temperature, and the mass of the water is same, that is 2 kilograms, and the specific heat of water is also the same. So here we put the water, we don't give a fire from the outside, and the full question is, we need to calculate the quantity of heat. So the mass of the copper is 0.5 kilograms of hot copper, and the temperature of the copper was 90 degrees Celsius. Okay, so 90 degrees Celsius is a change, is the temperature of the copper, and the temperature of the water is 20 degrees Celsius, and we know the specific heat of the two materials will be different, right? So for water it is 4186 joules per kg degree Celsius, and for copper it is 387 joules per kg degree Celsius. Now let's do this example. This question we will remember that the copper is going to cool down and the water is going to heat up. So this is going to cool down and this is going to heat up, and they will reach an equilibrium temperature. And this temperature is the temperature at which these two are going to meet. So they will have the same equilibrium temperature. These two heat will be the same, assuming that there is no heat is lost to the environment, because the entire heat, whatever the copper is losing towards the water, that quantity of heat is used to raise the temperature of the water. So no heat, we are assuming here that there is no heat that is lost to the environment, and it is an isolated system. Okay, if nothing is stored, then we'll assume that no heat is wasted out, the entire heat is transferred to each other. So what is the important trick here is that the Q of C, that is the heat which is lost by the copper, and the heat which is gained by the water, that is QW, will be equal to, net will be equal to 0, because one will be positive and one will be negative. So the total QC will be equal to minus of QW. Okay. This is very important trick that will use this question to remember. We will use for this question to solve. Okay, and here the same formula that we will use here is, so let's say equilibrium temperature is TF, that's the final equilibrium temperature. So both the copper and the water will have a final temperature of TF. So the water has an initial mass of 2 kg, it has an initial temperature of 20 degree, it has a specific value, a specific heat capacity, we know that specific heat. And similarly for the copper also, in the question it is given that is 0.5 kilogram, the initial temperature 90 degrees Celsius, and the specific heat of copper is provided. So here we can write down as, since QC plus QW is equal to 0, we know already QC plus QW is equal to 0, we can write here 193.5 TF, right, minus 17415 plus, so this is QC, and then QW is 8372 TF minus 167440 equal to 0. Right, here we can calculate TF. TF is only one variable that is present, so we can calculate TF as, you can simplify, I have simplified already, 184855 divided by 193.5 plus 8372, that comes out to be 21.58 degree Celsius. So this is our answer. So basically you are solving for TF by equating QW is equal to QC. So seeing the temperature, you can see that the water had initially, what was the temperature of water? It has only 20 degrees Celsius, and now it has increased to only 21.58 degrees Celsius, whereas copper was 90 degrees Celsius, 90, and it has reduced to 21.58. So what you can see, that specific heat of water is so high that we can add a lot of heat and it doesn't change its temperature much, right? So here the container must absorb some heat, but we have assumed, as discussed below, that we have assumed that it is an isolated system and hence it's not interacting with the environment.